Well, it looks like we're live again in CNBT 1311. All right. This is chapter 4 still, 4.13. All right. Precast concrete connections. The devil is in the details, they say. And these are detailed connections. Now, you as an architectural designer will be working with your structural engineer. This is what makes structural engineers not sleep at night, is these details. Every type of structural element requires its own particular unique detailing system. Now, we've already talked about these precast panels, and you pour the concrete deck up here, and the slab goes down into here, and some of the concrete flows back in here with the rebar. Assuming the contractor's doing what he's supposed to. These are called grout voids, blah, blah, blah. All right, so that's for our precast slab. Now, again, this is for completely pinned connections. You're not going to transfer any moment through this. All right, here's another precast slab detail. I particularly like this stuff where you're casting lugs in here. All right, now these come from a steel fabricator. We design these plates, and they're cast in with the column. Here is the corbel. This is called a corbel that this panel is setting on. Okay. This panel was cast at the casting yard with mating steel plate. Okay, and so when we set this on a high density plastic bearing pad, it's usually HDPE, high density polyethylene bearing pad on the corbel, so you're not having concrete on concrete. Just like up here, that had an HDPE strip. Do not get talked into using elastomeric rubber or some crap. Use HDPE. And then you'll come along here and you tack weld these things. You tack weld them together. Now, does that give you a moment connection? No, but that gives you a much stronger connection for shear. In other words, if the wind's blowing in this direction or earthquake load, it ties the building together. Okay. And it more closely allows these precast concrete panels to act as a diaphragm. Now, if you really wanted this to be a diaphragm, okay, you would have to put some kind of tying reinforcing steel together across all of these. I have seen these where the edges have a precast embedded steel plate, and they put a top plate across it, tack weld that when they assemble it, and then they come in and they pour their deck. Your mileage is going to vary. There's all kinds of ways you can be creative in how to tie all this together. A good creative structural engineer and an architect that works together can create some really amazing stuff. Now, here's one with traditional reinforced masonry. And if the masonry is not reinforced, you are asking for trouble. Then it just becomes brick veneer, like on a residential house. Okay, but this would be reinforced masonry, engineered reinforced masonry, and you handle it the same way. All right. All right. Here's another one. Here's a precast column or wall with a corbel, and you got an HDPE pad, and then you've got your top plates up here that you weld. Okay. Here's an inverted T. Remember what an inverted T is. It's a T upside down. This was cast in place on a job, or it could be precast and pre-stressed to come out with reinforcing ties coming out of the top. Normally these would be extra long, and then they'd bend them in the field. And this also has a clip plate in there with an embedded rod back in there with a tie plate coming into here, okay, to another structural T. Again, your creativity is only limited by yourself. And then you put your reinforced concrete topping. And this could be lightweight concrete, or it could be structural concrete as a topping. But remember, all of this has extra weight and has to be calculated from the very end of the building at the top, with all the rooftop units, your roof structure, everything, which would all go back down to what? The foundation, right? All right. So that would be a precast structural T, okay? Precast beams are handled the same way. They've got embedded tie plates, and throw an angle in there, and you'd weld this and weld that with a fillet weld. Oh my God, get your pen out. What are you doing? And that would be a weld. You'd weld it there, and you'd do a fillet weld there, and you might want to I don't know, let's just say 6011 rod, welding rod to be used. All right, most of that would be in the specs anyway, and you wouldn't have to put it on the details, but this is a welded joint to tie those together. Again, this does not give you moment. It gives you resistance to shear across the building. Here's one. This becomes more rigid, but I still, as an engineer, would not consider this a moment connection. But in the heavy industrial setting, you might need a top and bottom tie plate for the shear. And depending, here's a steel wide flange haunch cast into a concrete column that these are setting on. And again, your engineer and the architect and you are only limited by your imagination. So this would be a heavy detail for shear. Now, some moment could be transferred through here, but I would not consider this as a rigid connection when you're doing moment distribution in your structural framework. But that's an engineering thing and not building construction thing. All right, let's get on with structural steel framing. Structural steel framing works the same. It's post and column. Post and beam, column and beam. Just like wood or concrete. It's just the connection details are different because it's a different building medium, okay? They call these skeletal frames. Some people do. Ching uses that term up here. It could be left exposed, like in the Centre du Pompidou in Paris, France, the art museum. And some architects and structural engineers work together and make the exposed structural framing somewhat part of the architectural ambiance of the structure. Again, it's up to you and your creativity and your money to come up with what you want it to look like. All right. Here's a good point. You don't want some weird irregular shapes. It's best if it's a rectilinear of some sort. That's what he's trying to get across here, a regular grid. We talked about lateral wind resistance before with X bracing, shear walls, column. So here we have a bigger bay, and here we have a smaller bay. So this could be a light commercial building where these are office and inspection spaces, and these could be where the CNC machines are for a small machine shop, who knows, or automotive shop. And the outside could be skin, a light metal skin, or a window wall if you want to pay for all that air conditioning. And but you're going to need some kind of shear resistance throughout here someplace. And don't forget your deck, our roof deck. We could come in here with a heavy steel pan, weld the pan to your frame. And I'm getting ahead of myself because we'll talk about that in a little bit. And then pour reinforced concrete up here. And it becomes a diaphragm on top on your roof. Keep it from twisting. It would resist going this way or that way, or longitudinally that way, or even sideways this way. Your imagination is only limiting you, so understand how the medium works. It's no different than an artist that works in watercolors or acrylics or gouache. Now here's a metal pan deck, and we'll see that later. Okay, here's a reference to where it's at, chapter 4.22. Our steel beam and our steel girder. The girder holds the beams. These are bolted connections. This is not rigid. This is a pin connection. And this deck can just be laid up there and then intermittently screwed or tack welded, or it can be structurally welded depending on the gauge of the deck. And then the concrete can either be lightweight concrete or it could be actual structural concrete. All right, more steel details. You'll take a steel detailing class that will specifically deal with steel detailing. I think that is ARCE 1315. That's steel detailing. I taught that one semester. And then the structural detailing for wood masonry and steel is 1352, I think, ARCE. Well, anyway, if you're in the architectural design program, you'll end up having to take those. Let's see. When bearing on concrete, yeah, we talked about grouting before, these anchor bolts. See, this anchor bolt embedded. All right, this is your embedment link. All of this, we talked about your embedment link. And then this grouting. Now these shims, how do you take a column and plumb it? Everybody knows what plumbing is, right? Plumbing means it's level in the vertical. Okay. Makes it straight up and down. All right. Well, you shim this with metal shims, and then you come in here and you pack this with high strength, non-shrink grout, and then do your final torquing on those bolts. Torque specs on these bolts for these plates, that'll be in your structural specs. Let's look at some more structural framing. We talked about this in building, right? What is this? This is more rectilinear instead of square, right? So your lateral load carrying mechanisms are required in both directions. We got to take care of this, what I call stick and beam, column and beam system, because this is single bent, right? Remember the bent? Now if you put a diaphragm deck up here on top, then this whole thing could be a big plate up here, structural plate, and it would be one big bent out of some of these little bitty haunches. All right. One-way beam system. Okay. So you got girders and beams. It's one way. Okay. And you can have a two-way beam system. Look here, just much like a two-way concrete slab, you've got a structural element going longitudinally down the length of the building. And then you've got these structural elements that are going transverse to the longitudinal. This would be transverse. This would be longitudinal. And in this case, they're using long spanning members. These are joists. They could be a bar joist or a heavier structural joist. Okay. He makes a note here. you need to keep this back in your mind. When a large column free space is required, long spanning plate girders or trusses can be used to carry the primary beam, which in turn support a layer of secondary beams. All right. So if this is a long span, that's what he's telling you, you use a lighter weight, deeper. Remember, this is deep, and it's not a solid beam. And then you got your longitudinal beams. Now these would be welded or bolted, and through the top, preferably if you can afford it welded, I would weld it. That way it gets more rigid. And then I'm a big fan of rigid frames. When you're doing the steel's easy to make it rigid. Just weld it up. Get with your engineer and figure if you how rigid you need your structure. For the scope of this course, you don't need to worry about your K value of your frame. K is the stiffness, spring constant, basically. All right. All right, here's some basic steel shapes, just like we had them in concrete. This is an S shape. Now, does that look like an S to you? No, but it's called an S shape. Now, some people in the olden days, commonality would say that's an I-beam because it looks like an I. Okay, fine. All right, but it's really, in the world of engineering, it's called an S shape. You see these used for girders and cranes because the flanges are narrower than the web of the beam. So you'd have these rollers up here on a dolly, a trolley, right on both sides. And it comes down, and there'd be one over here, and this is where your hook would be, or your draw works to lift the load, and then this can run up and down the shop. So a lot of your overhead cranes are like that, where it's a single beam or all that out of the way. So this is called an S shape. S shape. Now this is a W shape or a W flange, okay, or a wide flange. It goes by many names in the industry, okay. This is a C shape or C channel, and this is structural tubing. Structural tubing can be seamless or seamed, and it can be square, it can be rectilinear, or it can be round. Like in the Centre de Pompidou, they use those giant round columns on the outside of that building, and they had their fire water was in there. They just pumped the freaking column full of water. As a part of their fire abatement system in France. All right, so you have structural tubing, you have a C shape or C channel. Now let's look over here and see what Ching wants us to look at. Rules of thumb for estimating depth. I love this, rules of thumb. Now what does a rule of thumb do for a designer? It gets you close. It doesn't get you out of the courtroom, but it gets you close in your original design, okay? So girders can span about the span divided by 15. Beams can your span, okay, divided by 20, okay, for estimating the depth. So let's say we had, I don't know, a 20 foot span, okay, divided by 20 is what? 1. So theoretically, for 20 feet, you could get by with a 12-inch beam, depending on the load. This is a rule of thumb, okay? And he already talked about the I-beam up here is your S shape and your C channels. Okay, so I already did that for you. All right, now the width is 1/3 to 1/2 of the depth, generally. If you go into the AISC manual, the American Institute of Steel Construction, which is the Bible for structural engineers when they're dealing with structural steel. We don't pretty much pay attention to that. We don't. I never did. I would look at the load and do my moment and shear analysis and figure out what my moments of inertia and my section modulus needed to be for the beam. And then we would just let this go where it goes. But generally, it's 1/3 to 1/2 of the depth. Your mileage is going to vary, so don't get all freaked out over that. Big thing you need to do as a designer is a rule of thumb for the span and the depth, okay? Because if this thing is like, let's just say the beam is going to be, and the girder is going to be, let's say the girder is going to be 36 inches, and the beam's going to be 12, okay? Okay? If this is your main long spanning girder, okay, and then this is your secondary, to carry this load in between here, and look, this is a multiple span, right? We talked about multiple spans. Then this is all going to eat up your height. So your height, your building height has to be bigger, right? Because you got to have room underneath it for people to walk and work and do whatever they need to do. So this will affect how tall that building is in, if it's a single story. And the same if it's a multi-story. All right, plate girders. I did some huge plate girders on the Hardy Toll Road years ago that spanned the Mopac Railroad Yard. If you've ever traveled on the Hardy from Beltway 8 up to 45, you went over that giant railroad yard, and you probably saw some weird-looking giant steel plate girders that came across, and they've been up like that, or some weird thing. And no, I wasn't on drugs when I did that. We had to do that because the railroad company would not give us permission to sink a column for a traditional short span rectangular plate girder. So these things are very deep, very long. They're outside of the normal spec of the length and depth ratio of a beam, and it was an award-winning landmark engineering feat. The things are deep, they're heavy, they got a thick flange on top, they're all welded up. They weren't hollow like these. Sometimes you can get by with making them hollow. All right. You can go in and cut sections to make them lighter. But these all have to be composite engineered. These, you don't go to the steel manual and just pick a beam based on the load. This is a very long, detailed set of calculations for your composite design. But that's the engineer's job, and a good engineer knows how to do that. And if he can't do that, or she can't do that, get you another engineer. All right. So bottom line, box girders, as far as you're concerned, they're built up by shapes. Now I drew a sketch like this of a wooden box girder, right? Remember the wood laminated, not laminated, but the plywood going between the 2x4s, and we did that in another chapter. We're going to revisit that here in a little bit. If we never get through these 40-something pages in this chapter 4. All right, that's all we're doing here, but we're doing it out of steel and not wood. All right, okay. Steel beam connections. Again, the devil is in the details. The devil is in the details. American Institute of Steel Construction, that is the Bible. That is the Bible that us structural engineers live by if we're using the medium of structural steel, okay? If it's concrete, we're doing the American Concrete Institute, ACI specs. If it's wood, we're using the building codes and the oh my gosh, I just had a AARP moment. The American Wood Institute or the American Plywood Association engineering manuals. Again, this is your engineer's responsibility, but it's also yours, because look at all the space it's taken up. All this has to have some place for it to go in your building design. So here's a pipe, round pipe column. Here's a regular, that looks like a H section. Could be a W section, but it looks like a H column to me. They're using double C channels. This is what caused the Hyatt Regency failure on New Year's Eve a long, long time ago. And contractor and an engineer went to jail over that because they were in cahoots. And they changed the design from this was the original design detail. They thought it would look cool. How the architect got away with this without going to jail, I don't know. But there were some people I know. I remember the court case. They went to jail. They changed it to this. So the main stress was not on the web of the C channels. It was out here on the tips of the C channel. And so when they had those thousands of people up there dancing on New Year's Eve on those elevated walkways that were suspended by these rods going up to the roof structure, these tips here, these tips, oh my goodness. Oh, you're pushing another button. Trust me, I'm a professional at this. Okay. These tips, they rolled with the stress. Okay. They rolled up right in here. And that bottom washer, since they rolled, these rolled this way in the weak direction because the strong direction, this is the strong part, this is the weak part. They rolled off and these floors collapsed with these people on them. And once the upper floors collapsed onto the bottom, the second level, then they all just fell down. The whole thing went down, several levels of the suspended walkways with all those people on it. A lot of people got killed and maimed and injured, and it was a big deal. Okay, we talked about rigid frames before. Stiffener plates welded to the column. I drew up some nasty details of this in another lecture. This you can consider to be a moment connection. This can transmit rotation from this beam into this side of the column, and same here. Both it does shear and moment. Here's another example of a moment connection. Now these moment connections, okay, here's a moment. We're talking about moment connections. All right. We're talking about moment connections. This is an AISC type 1 rigid frame connection. Now there are many of these different types. On the prefab rigid structures, they don't look like this. They'll build that column up and then bolt it to a heavy reinforced plate, and that's considered also rigid. They don't necessarily have to be welded. But this is, again, back to the world of engineering, okay? So you've got these stiffener plates, their original angle under loading by developing a specified resisting moment. And we all know what moment is. Remember, moment's just torque. It's a lever. It's that not crescent wrench. It's that ratchet wrench with that socket on that nut, right? Rotation. Also the rotation in this direction, in the weak axis, okay? Here's another one. This I call a suicide connection, okay? Even though these are stiffened, if this is bolted and it's just set on top, you got to be careful about this. Because if these aren't bolted good, okay, or, you know, if you're going to do this, you might as well just run a fillet weld there and on the back side and underneath here and along the inside face. That would be like that, okay? But this would come from a fabricator, and for the ease of construction on the site, then you might just do a lap joint and bolt it. Therefore, that's not a moment connection. This is not a moment connection, and don't let anybody tell you it is. If it's bolted through here, It's not a moment connection. It's a pin connection. It just happens to be stiffened. Okay? It's stiffened for shear. And he shows you a detail here of a prefabricated, at the steel fabricator, an opening to run conduit through it, or a water pipe. I personally think that's a bad detail for a water pipe. Conduit's one thing, but if you have to replace a water pipe, then you've got a deadhead in here that you've got to deal with. Your plumber's got to deal with. All right. So again, I don't expect you to detail these up. This is not a drafting class. I'm not going to ask you to sketch them. If this was a 16-week class, I'd ask you to sketch some of this, but we don't have time for that. All right. Here's some more steel beam connections. These are all pinned. These are all considered pin connection. It's good for shear resisting, but not for moment, okay? And if you came in here and welded all this up, you could make an argument that you're transmitting some rotation. But as you can see, this beam can rotate and not translate the rotation, because any rotation would be just along that plate. This plate is good for downward forces or upward forces. We call that shear. And for translation forces like from the wind or vibratory lateral loads from an earthquake. All right. So it does allow this to float a little bit, sort of like the Columbus bowls and the pagoda and the little snake dancey thing. Okay. All right. Here's a detail of angles as a clip, and then you're bringing in a side beam to a girder, main beam, girder. You got to come in here and you got to do a clip. The steel fabricator has to clip that. And then all of these will be numbered and assigned to an assembly drawing. And these are all trucked out to the job site. You look at your assembly drawing, and you start putting these together like a Lego set. Follow the directions from your fabricator and your engineer. And you may run into that as a designer. You may be sent out to a job site. Here's an example of a pinned connection for shear. It's called a seated connection. Why is it called a seated connection? Because it seats. Okay. Shear connections are AISC type 2. So you got type 1 connection, which is moment, and you got a type 2 connection, which is shear. All right. All welded connections are aesthetically pleasing, especially when ground smooth. Now, no one's going to ground these welds smooth. If your contractor is going to be one mad individual. These things are welded. You start grinding that weld off, it makes the weld weaker. Okay? Because when we do weld engineering, it's the area of that weld and the length. It's this area, cross-sectional area, and the length that goes into the calculation of how strong that joint is, assuming your welder is a good welder. All right. So I happen to like welded connections because if you can afford it. This takes a longer time to erect because you've got to bring these up, you've got to square them. Most of these welded connections have a pin clip like this to hold them in place while the welders go in there and weld these up. These things just don't magically just get stuck up there. All right. Here's a semi-rigid connection. This is an AISC type 3, semi-rigid. Symbol beam and girders possess a limited but a known moment resisting capacity. So it's semi because it's bolted and there's no cross reinforcement across here. So some moment can be resisted through here. And when the structural engineer is doing the moment analysis for the whole frame, this is taken into account. Again, as an architectural designer, this is outside of your normal architectural drawing stuff. But you may end up going to work for a steel fabricator, and you'll be doing hours and hours of fabrication detailing. Okay, open web steel joist. And we talked about girders, plate girders, with holes in them for weight reduction. Well, again, these are open web steel joists. Now, the common name for these is a bar joist, okay? But shop fabricated steel members having a trussed web, a K-series joist, has web consisting of a single bent bar, okay, aka bar joist in the commonality on the street in a zigzag pattern. All right, they're prefabricated truss is what they are. All right, just like those wooden prefabricated trusses you see for some of these wood framed construction projects, but these are flat. These have a lot of benefit. You can have a bayonet or an extension. I call it a bayonet. That can come out and at a point, and if this is sitting on a wall, that bayonet, then let's just say this is a structural wall, and what are we supposed to put up here? Oh, a bearing pad, right? Yeah, some kind of bearing pad. If it's a metal thing, we can weld this, and we can have an embedded steel plate right here where we can weld this bayonet, which would have a mating steel plate on it. And what would we have? We would be approaching a semi-rigid frame, would we not? See, again, this is an example of your imagination is only limiting what you can do. And now this is not going to be a rigid connection. This detail here, this would be pinned. And in the world of structural engineering, this thing would bend down, and we would think that, okay, it's pinned, okay? And how we handle this detail would resist the lateral shear from wind or earthquake, and of course it supports the downward or the upward if we had a high wind going over this and it wanted to suck the roof up. And the same over here. This joint gets to rotate, so it's not a moment joint, it's a pin joint. Even though it might be welded to keep it from falling off, it's still considered pinned, and this would be a simple span. All right, here's some rules of thumb for K-series. Now, your mileage is going to vary. The safest thing to do is you go to the manufacturer who makes these, and there's some manufacturers that make these little bar joists, and the same manufacturer makes some super heavy-duty joist with angle iron in here, and they're square and they're stout, but the manufacturer will tell you what they can span and how much load they can carry. All right, so but there's a rule of thumb: 8K1, 10K1 will go that span. A 16K5 can theoretically span from there to there, depending on what the loading is again. Okay, an LH series, these are long span joists. Okay, they're long span. And they're anywhere from 18 to 48 inches deep. And I've had some projects where I use some 4-foot deep of these things, and to span a large manufacturing facility. 30K is 32 to 60 feet in your spans. Okay. All right. Your 30 is your depth. Okay. All right, so, and he tells you down here what the designation is, okay? That's the nominal joist depth in inches. You got to consult the Steel Joist Institute. So here's another industry standard group that establishes, just like the American Institute of Steel Construction deals with hot rolled shapes, the Steel Joist Institute is like the American Plywood Association, the American Concrete Institute. It sets a standard for these prefabricated joist. All right, so this would be 32 inches nominal. This means it's a long, okay? It's the joist series, and this is the core designation. This all you go to their manual, you go to their catalog, and it's all there. Now there's a DLH series, deep long span joists are available. Oh my goodness, looky here, 52 inches to 72 inches, and can span up to 144 feet. Your mileage is going to vary. You get with your structural engineer. And I've used all of these in my career. I think there was some overhead walkways out of one of the big giant wastewater treatment plants where we had some 52-inch deep long span joist. I'm almost sure, but that was 69th Street over by the sludge dewatering building, if I remember correctly. But that was a long time ago. Long time ago. In a galaxy far, far away. Now, the benefit of these things, what's the benefit of these things? You can put a suspended ceiling in. I'm not going to read all of this down here. You read it, okay? Now, if you're going to go this route, you've got the benefit of putting a suspended ceiling, and that gives you some space underneath here for your HVAC system, your water, your sewage, your potable water. Potable means you can drink it, and electrical. Okay. If you're going to use a ceiling that's attached to this, then you got to run them up in here, and that means you got to go back to your manufacturer and figure out how big this space is. Because if you've got, let's say, a main 36-inch diameter HVAC duct, then you need to make sure you've got the space to put that circle in that triangle. Now, I think some of the neatest architectural designs are, like, there's a nice Italian restaurant that my wife and I like to go to. A little advertisement here for Mezzanottes over off of Louetta and Grant by Stone Cold Meats. Excellent restaurant. If you look up into their ceiling, all of this is exposed. All the structural stuff is exposed. They don't have a suspended ceiling. They've got their insulation up in here, and we have a chapter on insulation. And this is all painted flat black. All this is black. HVAC system, everything. And as an engineering geek, I love that because I get to go in there, and my wife, who's a master of wine, Wes at level 3, is doing her swirly thing and talking with the maitre d' about wine. And I'm sitting there going, yeah, okay, fine, whatever. Just pick the wine, I'll drink it. And that's the benefit of being married to a master of wine. I don't have to worry about the wine list. She takes care of that. Then I can look up in the ceiling and pretend I'm an engineer again and get all geekified over the mechanical and plumbing systems that are exposed. I think it's really cool. Go back and Google in YouTube the Centre de Pompidou in France. I have a video of that, and if I find it from back in 2018 and 2019 when I taught this face to face, I'll throw it up there for y'all's amusement. But it's a really cool design. They exposed all that structural steel. And the architect worked very well with the engineers, and it came off. I think it's cool. Now, some of the French think it's a blight on the Paris, but I don't think so. I think it looks massive cool. All right, so your spacing of joist is related to the magnitude of the floor load. And what did we talk about floor loading before? It's not just the live load and dead load, it's also the bounce, right? It's also the bounce. You don't want this to be a trampoline. So there's all kinds of things that go into effect. And this is where your engineer and the architect, the designer, must work together. That's why I'd be careful about these rules of thumb up here, about these spans. If you stay on the lower end of the span, yeah, you're going to be pretty safe. But if you start stretching the envelope, Well, let's just say that I got all froggy and said, I'm going to take this 16K5 and I'm going to run it all the way out to 32 feet. No, this engineer's not going to do that. If I've got a 32-foot span, I'm coming back down here to an 8, see if I can use an 18 or even a 22, okay? Because this is going to be deeper, it'll be stiffer overall. But that's up to you. You and your engineer and your budget, your owner, are going to have to make that balance. It's all a balancing act. It's all one big compromise. Floor deck spans and floor joist spacing. Okay, metal decking with concrete fill. This goes back to the diaphragm thing again. And I'll talk about this till the cows come home. If you're going to spend the money for a deck, and you're going to need a deck, keep the rain off, right, and the sun, then sometimes it's really economical to use a heavier gauge steel deck. Make sure it's welded to your joist up here, and then pour a reinforced concrete fill in it. It makes a very nice diaphragm, and it makes this a very stiff building, very stiff building. Doesn't mean it's a rigid frame, but it makes it stiff for shear and wind resistance. Going that way, and remember the wind blows this way, or it blows through here. So use your materials, don't waste them. It's just like if you're using plywood, tongue and groove plywood decking and wood framing. Go ahead and spend the extra money to glue it and screw it to them floor joists. You've just created one big giant diaphragm, and it'll make your structure a lot stronger. All right, what's he trying to tell us here? Okay, because of their standard depths and manufactured lengths, open web joists should span rectangular bays. What do you think? I mean, how are you going to make a round building out of this, right? Unless you go through the tangent and all the trigonometry and stuff that makes people sweat, have headaches. No, it's square, it's rectangular, right? All right, we talked about that before. Framing works most efficiently when the joists carry uniformly distributed loads, and that just makes sense, okay? And I love this. If properly engineered, concentrated loads may bear over the panel points of the joist. Okay, if it's properly engineered. Again, that goes to the use of the building. Okay, this image, we have a reinforced concrete or reinforced masonry wall here. All right, we've got steel beams or girders. He's repeating himself. You have a various form of roof decking. Yes, you can use precast panels. If you're going to use precast panels, make sure that they're the pre-stressed with the cores in them, because it makes them a lot lighter. And the thing about those pre-stressed cored panels that are manufactured at the plant, that concrete's put in super, super dense. So it's going to be lighter weight than if you tried to do this on site. Here's a tongue and groove roof deck. You don't see this anymore. This might be on the interior, like a floor in a residence. But I think if you're going to use wood subflooring, you're probably going to use 1-inch tongue and groove structural plywood. That'd be probably cheaper than this. But your mileage may vary depending on where you are in the United States. If you're like across the street from a wood mill that specializes in this, well, guess what? That's probably going to be your cheapest deal. Here is that heavy gauge steel deck that acts as a form for the concrete. We'll talk more about that later. And then this can be either lightweight concrete, Paralite, with wire mesh, or it could actually be treated as a structural concrete pour, which would create a diaphragm. All right. Now, these things here, these are tie reinforcements. This is what's called horizontal bridging or purlins or whatever. The industry, prefabricated manufacturing, building industry, they have names for these things that are into there, like purlins and this and that. But all this is a horizontal framing, okay? And they're welded to the top and the bottom cords. And what it's supposed to do is what? What's it supposed to do? It gives you diagonal bracing. Now this is diagonal bracing because it's an X brace. So we have X braces in here. This is just horizontal bracing. It keeps these things from rolling over. As the spans gets longer, these things, when they're loaded, load comes down. See how it's pinned up here? There's nothing to keep it from twisting down here. These things have a tendency to want to roll over. And we're not talking about major catastrophic stuff, but it could be if it's super loaded, it'll roll off of here and then collapse the roof, like that roof ponding that I talked to you about in a couple of videos ago. Yeah, it probably seemed like years ago, right? All right, this is diagonal bracing. You'll see this a lot. Sometimes they'll use horizontal bracing, then when they get out to the center, where the propensity for it to roll is greater, then they'll switch to diagonal bracing. This has to be spaced and engineered out because you're going to want to run what? You might want to run your HVAC system ductwork through these. All right? Okay. And they're welded or bolted, but all this, you can bolt or weld. This would be a detail for a wall. This could either be embedded into the wall, the concrete wall or the masonry wall, or a column, and you could weld it onto a steel column. And then you tie your diagonal bracing to that. All right. If you have an opening, just like in a pre-stressed concrete detail we saw earlier, you would have what's called a header or support, and you're bridging this. All right. This would be, let's say, let's extend this joist on out. Okay. Let's say we've got another one of those coming over here. And what would that be for? That might be for your roof curb to set on your deck. So your deck's going to be filling in here, and then the deck's cut. And what goes in here? This is where your RTU is, your rooftop unit. If you're using a traditional DX unit on the roof for your HVAC and heating system. All right. So that's where your RTU, rooftop unit, RTU. Mechanical systems is later on in the book. All right, but that's where your RTU would set. And it would be a curb. So let's go back to this deck detail up here. Something like that. You want to set, if this is your metal pan, and if you were my detailer, I'd fire you if you didn't do it like this. You're going to set the curb for that doghouse, for that RTU unit. Okay, here's that opening, bridger. All right, you're going to set it on the deck, you're going to tack weld it, and then you're going to put your waterproofing in here, and then you're going to pour the concrete, your roof concrete up here. Why is that? Because you're going to have more flashing that's going to come up here. They had nothing. The Cypress Center, that Lone Star built, they put the whole roof in, then they came in and cut the holes in the roof after it got done and set the curb on top of this. And they have leaked since 2013 when we first opened that building. And they have spent lots of money. Lone Star has spent a lot of money coming up here and reflashing this and reworking this and this and that. It was just a bad construction. All right? Bad detailing, bad construction. You want to do that curb on that deck and then pour the concrete and the flashing together so you have one monolithic watertight structure. If you do it like Cypress Center, it's going to leak. All right, enough of that. All right. Now, when he talks about limited overhangs, that's what he's talking about here. Okay. Now, those big DHLs and these LHs, you can get that bottom card to come out, and I've actually used them where I didn't set them on like this. The bottom card was a structural element, and I sat them across the top of the wall in a structural manner. But that was not generally how you normally do it. And then you could use this as a large overhang. So then that truss becomes, remember that span where you had two cantilevers and a single span? We talked about that, I think, in chapter 2 or 1. I don't remember. So basically, you have something like this. Now that is not the normal bar joist, and this has to be engineered. This connection has to be really looked at, or this thing's going to roll off, and you're going to have a bad, bad, bad life. All right, but this overhang can be engineered out, so it could be an overhang around the building for rain and stuff like that. Not necessarily the most economical thing. All right. So you can have limited overhangs on a typical K-joist. All right. That's up to you and your manufacturer. Now, I'll go back to the metal decking thing. All right. If this was going to be a diaphragm structural metal deck, then we're going to weld this deck. So you're going to come in here, you're going to spot weld it according to the Metal Deck Institute. And yes, there's another industry standard for making diaphragm decks. Every one of these low spots is welded to your main beam or your steel joist. Okay. And then your concrete floor or slab is then poured on top of this. And this metal decking can be stiff enough to actually act as your form, so you don't have to do any underjacking. Okay. Here's a super duper deal. This you see a lot on some bridges and some roads and heavy construction. This detail really is indicated of a lightweight concrete pour. This would be a reinforced concrete pour. All right, and this is what's called farm decking as opposed to just metal decking. Okay, so if you're gonna do a reinforced concrete diaphragm on top of this, then you would have to use a heavier gauge metal deck, and it becomes not metal decking, quote unquote, it becomes form decking because the decking is designed to support the weight of the concrete pour, including the guys that are pouring it and the gals and the Jersey buggies and all the construction loads. And yes, you may have to underpin this and jack it from the lower floor until this reaches its structural strength. Now, concrete will reach a 7-day strength and then a 28-day strength. At 28 days, theoretically, it's as strong as it's going to get, even though concrete still hydrates for years after it's poured. But that's material science, not this course. All right, composite decking. He defines composite decking as tensile reinforcement for the concrete slab. You have these that are spot welded to the deck and the beam. Again, the best thing is to go ahead and weld the heavy-duty deck. These serve as shear connections for the concrete you're pouring in, and there will be rebar coming out of here, trust me, or wire mesh fabric. There's no reason to throw away the structural integrity of what you're paying for. You might as well use it. Like I said, your imagination is only limiting you. All right. So in section, you would see something like this. These would extend up above this into the concrete pour. These are installed with a spot welding system after the deck's laid down and before the concrete's laid. This is what's called cellular decking. These are manufactured by either cold forming a lip, a plate underneath a formed steel deck, and it works as a diaphragm too. And these hook in. If you weld them to your framework, then they can be a composite deck. And depending on the structural integrity of this, based on the manufacturer, then you can probably use less concrete and less reinforcement. But that's between you and your engineer and your budget. Okay? Rule of thumb. Don't you love these rules of thumb? All right. Don't you love it? All right. Rule of thumb for overall depth, span divided by 24. You know what your span is. Span's between either the girders or the joist. And you take your span length and divide that by 24. You got to consult the manufacturer for patterns, widths, and lengths. Okay? Gauges is the thickness of the metal, and you may want to galvanize, you may not care. And allowable spans and loads. Spans and loads. They will tell you what the allowable loads are for their decking. All right, light gauge steel joists. Let's see where we are. Come on. Oh, we're already at an hour. Okay, we're going to kill this here. All right, this is going to be, what, 3? Yeah, this will be 3. All right, we'll pick up 423 on the third video. All right.